Hi, this is Dr.G.Vikas Paul. In this session, we'll discuss about the fixed beams. So, what is a fixed beam? A fixed beam is a beam with both ends fixed. So, both ends fixed. Beam with both ends fixed. So, at A and B, it is fixed. So, it is known as fixed beam. So, now fixed beams are also called as built-in beams. Built-in beams because they are built in the walls. So, built-in beams is the other name for fixed beams. Now, coming to degree of static indeterminacy. So, what is the degree of static indeterminacy? So here we can divide it into two cases. When there is only vertical load on the fixed beam, okay, vertical reaction at A will be generated, vertical reaction at B, and moment at A, moment at B. So as there is no horizontal forces, no need to take the horizontal reactions also. So we know that formula for static indeterminacy ds equal to r minus, actually it is 3, but here we are neglecting the horizontal reaction. So sigma fx is also neglected in the 3 equilibrium equations. So only 2 equilibrium equations. What are they? Sigma fy equal to 0 and sigma m equal to 0. So what are the total number of reactions? 1, 2, 3, 4. 4 minus 2. So ds equal to 2 for fixed beam with vertical loads. Okay. So now if we see for inclined loads, so degree of static indeterminacy for fixed beam with inclined loads, then we can consider the horizontal reaction also, because it is inclined loads, we can divide it to vertical and horizontal components. Okay, so ds equal to total 3 plus 3 vertical horizontal moment. So 6 minus 3 equilibrium equation, sigma fx equal to 0, sigma fy equal to 0, moment equal to 0. 6 minus 3 equal to 3. Then what is the degree of freedom here? We have the formula 3j minus r. So joints are 2. 3 into 2 minus total number of reactions 6. So it is 0. No degree of freedom. So it cannot move anywhere. Beam cannot move anywhere. Right? So here, coming to the deflection curve. So this will be deflection curve. At the supports it will be hogging. At the center it will be sagging. Okay. This is the case where a load is acting at the center. Means at the center it will be the maximum. Okay, negative bending moment hogging, positive bending moment sagging, again negative bending moment hogging. So it supports at A and B, slope is 0, deflection is 0. At here also, so theta is 0, y equal to 0. Okay, and it supports the type of moment is hogging at fixed ends. At center it is sagging. So first case, if we see fixed beam with eccentric point load, this is a fixed beam with eccentric point load. W is acting at A, distance of A from A. The total span is L. Find the final end moments, that is MA, MB for the fixed beam subjected to eccentric load. Now we need to find the final end moments MA, MB. Okay, so here the first step here is to convert the fixed support to simple supports and draw BMD and calculate area. So here what I have done, I have removed the supports and I have, in place of fixed end, I have kept simple supports. Okay, here also in place I removed it and kept simple support. And for this I have drawn bending moment diagram. We know that the maximum bending moment value for this case is WA by L. Now this area, how to calculate the area? A1 equal to half into base into height. Base is L. So half into L into height is WAB by L. So area A1 is half into L into WAB by L. Step 2 is to draw bending moment diagram subjected to fixed end moments. So for this fixed end moments MA, MB only we are taking here. For this the bending moment diagram is this one. So as it is W is acting here, it will be MA here, MB will be in this way. Okay, so here as it is not acting at center, as it is not symmetric, MA will not be equal to MB. MA is not equal to MB. So here calculate the areas of bending. Next step, calculate the areas of bending moment diagram for simply supported and first fixed end moments and equate them. So in the first case we have calculated area half into L into WB by L. Here if we calculate area of trapezoidal half into MA plus MB into L. So from here we can write MA plus MB equal to WB by L. Let it be for equation number 1. Coming to step 4, calculate the moments of bending moment diagrams about fixed ends. Suppose here A I am taking about A, bending moment due to simply supported beam, okay, is equal to bending moment due to fixed end moments about A. We need to equate. For this, first we are calculating bending moment due to simply supported beam. For simply supported beam case, the bending moment diagram is this, we know. Okay. Now calculate bending moment about A. Let us calculate bending moment about A. Okay. Now first let us divide it into two triangles, first and second. First, what is the area? What is the load? Half into A into WAB by L. Half into A into WAB by L. Where it is acting? At centroid. So what is this distance? What is this is centroid. Okay. What is this distance? 2 by 3 times A. 2 by 3 times A from A. Okay. Plus this one. So what is this area? Half into B into WB by L. Now what is the distance of its centroid from A? B by 3 plus A. B by 3 plus A. If you solve it, you will get the second equation. Now bending moment due to fixed end moments about A. So this is the this bending moment diagram. Second case, second step bending moment diagram. This is the first step bending moment diagram. Now calculate. We should calculate bending moment due to fixed moment about A. So I will divide it into two parts. First part, second part. What is the area of first part? Half into L into MA. Half into L into MA. What is the centroid? Centroid will be here. L by 3. Okay, total is L. This is L by 3. Plus, now second portion. What is the area? Half into L into MB. Half into L into MB. Now where will be the centroid? Centroid will be somewhere here. 2L by 3. 2L by 3. If we solve this, we will get equation 3. Now equate 2 and 3. If we equate 2 and 3, we will get this one. Okay. Now this is a simplification process. What we have done here, we have taken 3AB plus B square divided by 3. 3 into 2, 6. In this step, we have taken WAB by 6L common. So 2A square plus 3AB by plus B square. Now we know that L equal to A plus B. Therefore, A equal to L minus B. So instead of A, I have written L minus B here. Wherever A is there, L minus B. So I have simplified it, L square plus B square minus 2BL. This also I have simplified. So after I have multiplied it, now what we have done here, simplifying, we will get this one. Then taking L common, we will get 2L minus B. Then WAB by 6 into 2 into, again I have substituted, instead of L, I have substituted A plus B here. So I have got WAB by 6 into 2A plus B. So left hand side is as it is equal to this one. Let it be equation number 4. Okay. Now let me subtract equation 1 minus equation 4. What is equation 1? This one. So if I do equation 1 minus equation 4, left hand side minus left hand side, right equal to right hand side minus right hand side. If I do, I will get this one. Then from here, if I solve it, I will get minus MB equal to this one. If I solve this, I will get this one. And finally, we'll get MB value as WA square B by L square. This is simplification. Okay. Now, substituting MB value in equation 1, that is in this equation, we can get MA value as WB square by L square. Okay. So now, so fixed end moments MA, MB we have calculated, that is WAB square by L, MB is WA square B by L square. Okay. Now let us see this case, fixed beam with point load at center, that means A equal to B equal to L by 2. So in this equation, if I substitute A equal to B, A equal to L by 2 and B equal to L by 2 in this MA and MB values, for this case I can get the value of MA, MB. So if I substitute in MA in place of AL by 2, BL by 2, I will get WL by 8. Same, if I substitute here, I will get WL by 8. So this will be the bending moment diagram for fixed end moments. This will be the bending moment diagram for simple supports. Simple support. Now I need to calculate Y max, maximum deflection. Okay, first when there is load, point load at center, I need to calculate Y max. This is the deflection curve. How to calculate? Simple. I will take a section XX. This is a free body diagram. Okay, I have not included HA because there are no horizontal loads. So vertical reactions and moments I have shown in free body diagram. I have taken section at this mxx. I need to calculate the moments. So if I calculate the moments, to the left side I have RA into x clockwise. So plus minus MA is anti-clockwise, therefore minus MA. But from a differential equation, we know that m equal to ei d square y by dx square from double integration method or Macaulay's method. So in place of this one, I have written this one. This is as it is. But here in the place of Ra, I substituted W by 2 because we know that when there is load, W reaction Ra and Rb will be equally distributed, symmetric load. So W by 2, W by 2. Ra is W by 2 minus Ma already we have calculated W will be 8. So integrate in this equation, we will get this equation and we will get constant. Now how to find this constant? Using boundary conditions. What are the boundary conditions for fixed beam? If I take any section xx, this is x from A. At x equal to 0, that means at A, slope is 0, deflection is equal to 0. At x equal to L, that is at B, slope is 0, deflection equal to 0. Okay. Now substituting x equal to 0, theta equal to 0 in this equation, I'll get C1 value as 0. Substituting C1 equal to 0 in this equation 2, I will get slope equation. This is the slope equation number 3. Now integrating slope equation, I will get deflection. I will get in terms of deflection equation, but I will get a constant extra. Okay. Now here this is equation number 4. How to find C2? So I will substitute another boundary condition x equal to 0, y equal to 0. So if I substitute x equal to 0, y equal to 0 in this equation, I will get C2 as 0. Substituting C2 equal to 0 in equation number 4, I will get this deflection equation number 5. Now when I get deflection equation, I can find a deflection wherever I need. So I need y max. So for symmetric load at center, it will be the maximum deflection will be there. So substitute x equal to L by 2 in this equation. So y max, y will become y max, x L by 2, wherever x is there, I substitute L by 2. So after simplifying, I will get y max as minus WL cube by 182 EI. Let us discuss the next case. Analyze the fixed beam carrying UDL, that is find MA, MB and deflection, maximum deflection. So when there is UDL on the fixed beam, okay, this is a figure, length L is the length. First step is to convert the fixed supports to simple supports and draw the bending moment diagram and calculate load. So I have removed these supports, I have kept simple supports. And this is the bending moment diagram. Maximum bending moment diagram is WL square by 8. It is in the shape of a parabola. So what is the area formula for the parabola? Area is 2 by 3 into base into height. 2 by 3 into L into height is WL square by 8. So A1 is WL cube by 12. Second step, draw BMD subjected to fixed ends. So for this fixed ends with UDL, so I have drawn the bending moment diagram. So as it is symmetry, MA equal to MB. Okay, now area A2, length into breadth, L into MA I am taking. MB also I can take, L into MA into L. So in step 3, equating the areas, A1 equal to A2. So when I equate, I will get MA equal to WL square by 12. Now in step 4, calculate clockwise and anti-clockwise moments about A and equate them. So first of all, I have drawn free body diagram here. I have removed the supports and I have shown the reactions and moments and reactions here. No horizontal reaction because no horizontal load. So here about A, I am calculating clockwise moments and anti-clockwise moments. So this is clockwise moment about A. See here. So what are clockwise moments? MB and this load into perpendicular distance. So MB plus WL into L by 2. Next is equal to, now anti-clockwise moments, MA and RB into L is also the anti-clockwise moment. Okay, as MA equal to MB, I can cancel MA, MB. Here I will get, if I simplify it, I will get RB as WL by 2, which is equal to RA. So RA, RB I have found out. Why I need to find out this? So MA, MB already I have found. Now I need to find deflection. For that I need reactions. Okay. So now I have taken a section XX. Okay. At this point I have calculated the MXX, RA into X minus WX square by 2 minus MA. Okay. Now this is equal to EAD square by D square. So integrating this equation, we will get C1, same as the previous procedure. I have substituted the boundary conditions x equal to 0, theta equal to 0, then I have got C1 equal to 0, then again I have substituted, I have got slope equation, again integrating this I have got C2 to To get C2 value, I substitute x equal to 0, y equal to 0. Okay, then I substitute C2 equal to 0. Then I have got deflection equation. Now to find y max, I will substitute x equal to L by 2. So if I substitute x equal to L by 2, after simplifying, I will get y max as minus W power 4 by 384 EI.